Hey there, folks, and welcome to another episode in the Geology 101 Physical Geology video series. I am Geology Professor Shawn Willsey. Thanks for joining me. Today, we are going to delve a little bit further into the study of earthquakes by looking at earthquake location and magnitude. This Geology 101 video series is modeled after my college course, the same curriculum, the same content you would get as if you were sitting right there in my classroom. If you'd like to support this series and you're enjoying what you're watching here, you can go under your video viewer and there's three little dots there. If you click on that button, you'll get an option for a thanks and you can donate that way, or you can go under the video description and there's a few links listed there where you can donate or send some support to the cause. Let's get right to it here today. So last time we spent some time looking at seismic waves, kind of getting into the nuts and bolts of where earthquakes occur and what earthquakes actually are. Today what we're going to do is we're going to look at understanding where earthquakes occur in terms of figuring out their location, how we actually can determine the location of an earthquake. And then we'll look at different scales that tell us how big the earthquake is, the magnitude or the intensity of the earthquake. So let's start right off here with the definition. The focus of an earthquake is the location inside the earth where the earthquake actually was originated. So where the fault movement took place and where that seismic energy was released, that's what we call the focus. You can kind of think of it like a little bomb going off inside the earth. It releases energy. Those seismic waves radiate out in different directions. And so we can have different depths of our focus. And so we broadly classify them as shallow, intermediate, or deep with these sort of crude classifications here. These, of course, a lot of times relate to plate boundaries. And so we do see some relationships between the depth of an earthquake and the location of the earthquake in terms of plate boundaries. So we typically see divergent boundaries containing almost entirely shallow focus quakes. Same thing with transform plate boundaries. And then our convergent boundaries, more specifically our subduction zones, where one plate's diving beneath the other. That's where we actually see quite a variety in terms of the depth of the focus. Now, when I look in here, when I hear on if I get an email alert or I hear a news item about an earthquake and they maybe tell me the magnitude or something about the size and the location, the very next thing I often want to know is the focus, because very deep earthquakes don't tend to cause as much damage as shallow earthquakes. So the bad news here for humankind is that all three types of plate boundaries can produce shallow focus quakes. And because humans are up here on the surface, that presents a problem because a lot of that seismic energy is focused, or no pun intended, or is concentrated on that area at the surface because those earthquakes are not too far underground. We use a different term to refer to the location directly above the earthquake, basically the map location of the earthquake, and that's the epicenter. That might be the term you're a little bit more familiar with, is the epicenter. So if they say the epicenter of the earthquake was, 50 miles east of Los Angeles, that's the location on the map. But it doesn't tell us the whole story, because we should also be interested in knowing how deep the earthquake was, because that's going to help us understand the possible damage that might occur from that earthquake. And we'll circle back to that here in a bit. I have a link I am going to share in the video description. I'm not going to show the video here because I'm not sure if I'm allowed to, but there's a great educational group that puts together different videos about earthquakes and seismic instruments and all sorts of things related to earthquakes. And I'll put a link on there that relates to how we understand the three-dimensional motion that comes from an earthquake and how we actually measure that with these seismometers or these seismograph stations. So go ahead and look for that under the video description. They do a great job in that 2 or 3 minute video of explaining it. So moving ahead, what I'd like to do now is focus on the readout, the actual the printed record of the earthquake's seismic energy passing past a location, going past a location. This is what's known as a seismogram. So as we learned in our first episode, there's the P waves or primary waves, the S waves, and then the surface waves. So these three distinct sets of seismic energy waves can be recorded on a seismogram, and then we can analyze them. Turns out, as we look at map location for the earthquake, the two most important parameters are when exactly that P wave first arrival is. So you can see that little deflection there on the seismogram lets us know that the P wave has hit this recording station. And then similarly, we see another arrival of the second group of seismic waves, or the S waves. And if we can figure out when that occurred, which this is time, this component here working its way across the seismogram. If we know exactly when the P wave first arrived and when the S wave first arrived, we can subtract the difference between those two, because the P waves are always faster than the S waves, as we learned in the previous episode. And we can take that interval, the P-S wave time interval, we can take that number of seconds, or it might be minutes, and we can turn that into a distance from that specific station to the earthquake's epicenter. So what we're doing here is we're learning how do we know where the earthquake occurred? Now, in today's world, the computers are incredibly rapid at telling us, right seconds after the earthquake's begun, sometimes, where the earthquake's location is. But let's look at the science a little bit behind. How do we know exactly where the earthquake's location is? But this is the first bit of information here, the difference between the arrival of the P wave and the first arrival of the S wave. If you know that time difference, which you should be able to figure out on your seismogram, there is some simple ways that I'll show you here in a second to turn that time into a distance from this specific station to the actual earthquake epicenter or focus. So let's use a fun example here to see how this might work. So let's say we have three good friends, Joe, Max, and Anna, and they all have seismograph stations. They all have seismometers. Santa was good to them that year for Christmas, and they got a brand new shiny seismometer sitting under the tree. Fantastic. And they all, you can see where they live here, a little bit of scale. They all live in this region, and they all record an earthquake. And so they all record the same earthquake. And let's say Joe records an earthquake, and he measures the time interval between those P and S waves. Turns out it's about a minute. And he turns that into a distance, and I'll show you how he did that here in a second. Turns out that the distance is 1,000 kilometers. So how would we know exactly where the location of the earthquake is relative to Joe? Well, all we know is that it's a distance of 1,000 kilometers from Joe. So we would plot up a circle with a radius of 1,000 kilometers. So here's Joe's location with the star, and with the circle of radius 1,000 kilometers. Somewhere along that circle's perimeter is where the earthquake occurred. But we still don't know exactly where the earthquake is. Luckily, Joe has friends, and so he calls up his friend Anna, and Anna recorded the same earthquake. However, the time difference between the P and the S waves at her location was 1.5 minutes. And so that corresponds to a different distance, and let's just pretend that's 1,500 or so kilometers. So at Anna's location, we do the same thing. We draw a circle with a radius representing the distance, 1,500 kilometers. And now, do we know where the earthquake's location is? Some of you might be saying, yeah, it's right where they overlap, but it can't be in this area, because if it's anywhere in this region, it's not 1,000 kilometers from Joe, and it is not 1,500 kilometers from Anna. So the location either has to be this location where those two circles intersect, or this one over here. So we've narrowed it down considerably from just this huge circle perimeter around Joe to either this location or this location. Well, we still don't know for sure, so what we need is a third source, a third friend, and that's where Max comes in. Max recorded the same earthquake. The P-S wave interval was 2 minutes. That corresponds, let's say, to a distance of 2,000 kilometers. So we draw a circle around Max's location with a distance or radius of 2,000 kilometers. And now you can see we get this all three circles intersecting at one common point, and that lets us know where the epicenter is. So this is exactly how earthquakes are located. Now, in the old days, I imagine they had to plot up circles on a paper map, and it took a few minutes to do. And nowadays, the computers and the computing speed is very rapid, and it can determine that epicenter quite quickly. Pretty awesome. So there's the epicenter of the earthquake. But before we move on, what about depth? Have we actually been able to determine how deep the earthquake is? So on our map, we know where the earthquake is relative, especially to Joe, Max, and Anna's location. It's right here. But do we know how deep that earthquake is? And here's where you have to change your thought from two-dimensional thinking on a map, just circles on a map, pretty easy, right? There's all three intersecting. This is called triangulation. It's exactly how your phone using satellites is able to know where you are and locate your position. But we actually do know the depth, because instead of thinking these as circles, this is where you got to use three-dimensional thought. Don't consider it as a circle around Joe. Think of it as a sphere, or in this case, really a half sphere or a hemisphere, because above Joe up into the sky, of course, earthquakes don't happen in the sky. They're below the Earth's surface. So it's really a half circle, or think of a bowl, like a cereal bowl, or if that helps. So if you consider Joe's location and Max and Anna's location, and think of these circles not as circles, but actually three-dimensional spheres, then not only do we have an epicenter, but we would also have a focus as well. We would actually know where in the Earth's surface, at what depth this earthquake took place. So that's a little bit on how we locate earthquakes using seismic information. Okay, so I told you I'd show you how we determine this PS wave thing. So here's a simple graph, and there's similar ones that are used often, but this basically shows us two things, the P wave and the S wave. So there's the travel time of the two waves, and here's the distance. So notice here, if we start at the origin, the earthquake has begun and the P wave races ahead. In fact, 2 minutes into the earthquake, the P wave's almost moved 1,000 kilometers, whereas the S wave's still lagging behind because it's always slower. Okay, so you can see the further the distance is between these two waves, the greater the time difference is. Notice 1,000 kilometers away from the epicenter, the PS wave time interval is about 2 minutes. If we move further away, maybe like 3,000 kilometers, notice it's 1, 2, 3, 4. It's almost 4.5 or so minutes out here. By the time you get out to this point shown by the red line, it's maybe 5 minutes. And so we can take that time difference, okay, between the P and the S waves, and then turn that into a distance using a graph similar to this. Pretty simple, really. Pretty fun using the graphs and the math all put together. So that's a little bit on earthquake location. Let's talk a bit here about how we measure the actual size of the earthquake. And we actually use two different terms, but they mean very different things. Of course, the one you're most familiar with that we'll get to in a second is magnitude. You often hear the first thing we hear about an earthquake was, oh, there was a magnitude 6.2 earthquake, and then the location. Those are usually the very first bits of information that are relayed in a news report about a given earthquake. But we actually have two ways to look at earthquakes. We have something called intensity, which is a qualitative measure of how much shaking has occurred. And this is normally based on primarily personal counts and damage that we see. So we can assess the size of an earthquake partly by looking at its magnitude, which we'll get to in a second, but also by looking at how much damage it did. How bad was the shaking? Maybe at one person's house, the shaking was substantial and there's damage in the home and the person is really rattled and there's a lot of anxiety in that person. And we might move a mile away in the same town and talk to another person that says, hey, that earthquake wasn't so bad. There was a little bit of shaking and a couple books fell off my shelf, but my house is in really good shape. I'm not personally super alarmed. I didn't get hurt or injured. And we might see differences like that depending on location and some other factors as well. So the other thing we do is look at the magnitude. And the magnitude, of course, is more of a quantitative measure of how much energy was released in the earthquake. So this is the same for any given earthquake. Now, sometimes you might hear an initial report of, it was a magnitude 6.8 earthquake, and then minutes or hours later, that maybe gets downgraded or something like that. That's because we're just taking that initial computer assessment of the earthquake, and then later a seismologist goes in and looks at all the data and pins it down and gives it a much more precise number. But usually it's fairly close. But the difference here is one is based on location, people's accounts, damage, more of the human element, if you will. Magnitude is purely math and science. We're just looking at how much energy the earthquake released, and so that typically will not change. So if the earthquake was magnitude 6.2, doesn't matter where you are, it's a 6.2 earthquake. Okay, now if you're further away from the earthquake, you might be feeling less of the earthquake's effects, but the magnitude is a specific number for that given earthquake. So both of those are helpful. They both provide useful information, but it's just different. So let's look at the intensity scale. The intensity scale we use is called the Modified Mercalli Intensity Scale. And we use Roman numerals instead of numbers to differentiate it from the magnitude scale, which does use numbers. So it goes from 1 to 12 using Roman numerals. And there's a lot of variability here. The intensity of an earthquake doesn't always go hand in hand with the magnitude. Now, typically, the greater the magnitude, the intensity goes up with it. But we can see instances where there's some big differences. So here's two earthquakes here in the U.S. This was the 94 Northridge, California quake in a large urban area outside of Los Angeles. Here's the Nisqually quake. I think that was, oh boy, now I can't remember, 2001 or 3 or 2, somewhere in the early 2000s. Doesn't matter, but similar magnitude, 6.8, located, southwest of Seattle. But notice the two shake maps or the intensity maps. Notice the darker shades of orange and red here in Northridge, and you just don't see a lot of those colors over here, even though it was a tiny bit bigger in terms of magnitude. Well, it turns out that this one had a much shallower depth. So the depth of the earthquake is going to play a big role in the intensity or the shaking. Other factors that might come into play could be the subsurface materials, areas that have solid rock under them versus areas that are underlain by soft sediment, or might be a high groundwater table where the shaking is actually enhanced and becomes much larger. Could be the construction styles of the buildings and infrastructure in these urban environments. I got a typo there. That should just be materials, not materials with an M. Sorry about that. But yeah, you could have one place with wood frame construction, another place with brick or adobe. Again, we talked about the depth, could be the population density. All of these factors play into the intensity scale. And I'll circle back here and kind of do a case study comparison between two fairly recent earthquakes and looking at them in terms of magnitude versus intensity. So let's look at the magnitude scale when it comes to an earthquake. And of course, most people have heard of the Richter scale, invented by Charles Richter, I think in the mid-1930s. He was just looking a way to measure and compare earthquakes in the Los Angeles, Southern California area, comparing one earthquake to another. Because up till that point, we really didn't have any sort of good way of measuring the size of an earthquake other than looking at maybe the damage that was done. So he came up with a way of looking at earthquakes, and it's a simple way. It basically takes, remember our seismogram? He just says, hey, find the largest seismic wave on your seismogram, which will typically be your surface waves. Measure that amplitude with your ruler in millimeters. And then I'll show you here how you actually can figure that out. And then basically by measuring that largest seismic wave, you can determine the size of the earthquake on the Richter scale. Now there's no upper limit theoretically to the Richter scale. You can go into the negative numbers, you can go into the positive numbers as far as you want to go. And it's a logarithmic scale. So it's not a linear scale. As you go up one number on the Richter scale, it's a 10-fold increase in the wave amplitude. So a magnitude 6 earthquake has 10 times the wave amplitude as a magnitude 5 earthquake. If you assess the earthquake in terms of full energy, the energy released from that seismic event, it's actually a 32-fold increase from one number to the next. So a magnitude 6 is 32 times larger in terms of energy as compared to a magnitude 5. And so using the Richter scale, the biggest earthquake we've ever measured using fairly modern seismic equipment since the Richter scale was invented, was an 8.9 in Chile in 1960. Now, if you're already kind of looking at that number and ready to type in the comments, hey, I know there was one bigger than that after 1960, hold your horses just for a second and let me get through all of this here, and then you can see where we're at here. This is just using the Richter scale. So the biggest earthquake on record using modern scientific equipment comes out to an 8.9 on the Richter scale. That was Chile in 1960. This is a simple way that he used to figure out the size of the earthquake. So let me walk you through this. And these are small numbers, I apologize. But here's a seismogram up here, P wave, S wave, surface waves. Basically, again, measure the largest seismic wave. So in this case, measuring the largest seismic wave, let's say it comes out to 23 millimeters. So over here, you have a simple scale of amplitude of the wave. Over here, because you want to correct for how far away the location is that the seismogram that is recording relative to the earthquake's location. So we're going to take that SP time interval, or we can just take distance. So either one. So if you know either one of those two things, and you measure the wave's amplitude, obviously the further away you are, the smaller the amplitude. If you're right on top of the earthquake, those would be quite large. But basically, by lining up those two endpoints here, it passes through a middle scale that gives us magnitude. So in this case, if we had amplitude of 23 or so millimeters on our seismogram, and we had about a distance to the earthquake of a little over 200 kilometers, by lining up those 2 points and drawing a straight line, that would give us a magnitude of about 5 on the Richter scale. So a very simple way to do it, very ingenious. And for many years, that was a great way for us to measure earthquakes. But there was a problem. There's an inherent problem that we realized not too far after the Richter scale was put in place. And the Richter scale, again, he was just trying to compare local earthquakes. He wasn't necessarily intending it to be this global way to measure earthquake sizes. So what I've done here with my terrible handwriting is drawn my own seismogram. So there's the P waves, the S waves, and then the surface waves coming in. This is earthquake number 1. And I want you to look closely at earthquake number 1 and earthquake number 2 and compare these two. Now, I've tried to, as best I can, draw the amplitude of the P waves, about the same. The S waves amplitude should be pretty close, and the highest amplitude of the surface waves from here to here and here to here. I didn't pull out a ruler and measure it, but just optically, just eyeballing them, it looks like it's about the same. And remember what the Richter scale says to do. The Richter scale says find the biggest wave, which is typically a surface wave, measure it, plug it into that simple little thing I showed you before, and there you go. There's your magnitude. So notice if we use the Richter scale for both of these earthquakes, we would get the exact same magnitude. Let's say, I don't know, 5.6, whatever. Doesn't matter. But what do you notice that's different about these earthquakes? Earthquake number 2 had sustained shaking. These surface waves were coming in with high amplitudes over some period of time, whereas in earthquake number 1, the surface waves came in but then dissipated quite quickly. And so it stands to reason then that if you had to guess which was the more substantially larger or more destructive earthquake, you'd probably pick earthquake number 2, because the level of shaking from these large amplitude surface waves goes on for a lot longer. That's harder on the buildings and the infrastructure that's trying to stay put. So earthquake number 2 is larger than earthquake number 1 in terms of energy, and yet the Richter scale will tell us that they're the same. So there's a problem with the Richter scale. For very large earthquakes, it works fine. For small earthquakes, you know, it works well. So all we've done basically is tweak it a little bit. The problem with the Richter scale is it does not do a good job of measuring the magnitude of exceptionally large earthquakes, where we have faulting over a large distance, large displacements, and energy being dissipated over longer periods of time. And so we've tweaked the Richter scale, and the scale that actually is preferred above the Richter scale is what's called the moment magnitude scale. And oftentimes you'll see a difference. You'll see the big letter M, but if you see a second smaller letter, if it's an L, that's Richter scale or local. And if it's a W, and I can't remember what W stands for, I'm sure someone else does, that is the moment magnitude scale. It's a better way to measure big earthquakes, and it accounts for all the total energy of the earthquake, not just the one big wave. So remember that 1960 Chile earthquake that I told you is the biggest one that we've measured in the last 100 or so years using modern instruments? It was an 8.9 or so on the Richter scale, and some of you were probably scratching your heads and you're like, wait a minute, there was the 2011 Japan earthquake, there was 2004 in Indonesia, there was an earthquake in 64 in Alaska, and you knew all those were bigger than 8.9. Well, here is the Chile earthquake with a better measure of its true energy. It comes out at 9.5, and that's a huge earthquake. I'll show you how much bigger that quake actually was than some of those other nearly equal but not quite as big earthquakes that took place in the last 100 or so years. Okay, so hopefully that helps you understand a bit about earthquakes in terms of magnitude and intensity. Oh, here's my graphic here to show you the energy level. So that 9.5 quake in Chile in 1960, if we represent the energy released by that earthquake with this big red circle, let's compare it to the Prince William Sound earthquake in Alaska in 1964. Again, a huge, historic, catastrophic quake. That would be represented by this circle. The biggest earthquake of my lifetime, I was born after both of those quakes, so the biggest earthquake so far on planet Earth in my lifetime was this one in Indonesia in 2004. The Great Sumatra earthquake, 9.1. This generated a tsunami that went across the Indian Ocean and killed something like 250,000 people. Right on its heels was a big earthquake in Japan, a 9.0 in 2011. And then we get to smaller quakes here. And then, interestingly, the smallest one shown here, and we'll talk about more about this quake later on, the Haiti quake in 2010, which was only a 7.0. I mean, really much smaller than all these other ones. And yet, tragically, this was actually a very destructive and fatal earthquake. So there's earthquakes by size, earthquakes in terms of their how often they occur. So magnitude over here on the left, and then right here in the middle, these numbers are basically averages of how many we see per year on planet Earth. So magnitude 2 earthquakes, tons of them. There's 1 million or so of those happening all over the globe. So those are very common. Magnitude 7 earthquakes, we might get about 20 in a given year on average, right? So that's a very much more rare event. Magnitude 8 level, maybe 3, depending on the given year. Magnitude 9s, it's less than 1 per year. It's usually, one every, 30 years, 50 years, something like that. So what you can see here is a simple relationship that is common in most Earth processes, and that is as you go to higher magnitudes, higher and more energetic events are less frequent, right? Small energy events, small little magnitude 2 earthquakes all the time, but more massive earthquakes that need to store up and release a lot of energy, those are much more rare. And then over on the right here, if you need another sort of comparison for their size, just the energy equivalents of different kind of common things we might have a reference on, the Hiroshima bomb, Krakatoa eruption, and how those would kind of fit with the energy release of these different earthquakes. So fun little thing from the USGS there. Okay, so winding down, looking at this is a case study, looking at 2 quakes, Haiti versus Chile, both the same year, 2010. Looking at their magnitudes, look at the big difference here, 8.8 versus 7.0. As you've seen with that previous diagram with those huge circles, this is way bigger than this one. I mean, by hundreds of times potentially. The Chile quake was way bigger than the Haiti quake. There's their depths. But now look at the interesting thing. Even though the magnitude was much more massive in the Chile quake, look at the intensity level and then look at the deaths. So the deaths in Haiti were approaching 250,000 people, just horrendous numbers here, as compared to about a little over 500 in Chile. The intensity level was high in both, but it was much higher in Haiti, even though it was a smaller magnitude quake. So what this gets back to is, you can't always assume that the higher magnitude quake is the most destructive, because there's plenty of instances in history, such as this one, that would show us that that's not the case. Now, why? Well, look at the depth. There was a bit of a difference in the depth. The Haiti quake was shallow, and shallow quakes are always going to be more destructive than deeper ones. Now, these aren't too big of a difference, but might have made some of the difference here in terms of intensity and deaths. The other factor here was the construction styles, the type of buildings in Haiti, which is a largely underdeveloped country with poor building codes, and they often get hurricanes, so they often tend to build roofs that are heavy, that can withstand high winds and storms, but those are terrible in earthquakes, and there was collapse. A lot of this earthquake took place right under the capital area, so there was a population density component. So I think the depth of the earthquake, population density, construction styles of buildings, those all were big factors as to why we see such a big difference here in these 2 quakes. So okay, last thing, the quiz time. Let's do a quiz question to round out this episode. So what we have here is we're going to compare 2 earthquakes. We've learned about magnitude, and we've learned it's a logarithmic scale. So a magnitude 6.2 earthquake releases how many times more energy, or how much more energy, than a magnitude 4.2 earthquake? There's your options there. So if you need to pause the video and think about it, or do some complex calculations, go ahead and pause the video. Okay, let's go to it. So the first thing you want to do here is subtract the numbers. So 6.2 minus 4.2 gives you 2, which you guys probably all figured out quite easily. Then it's a question of what to do with that 2. Do I times it by 32? Because you remember, hopefully, that when you go from one number to the next on the the Richter scale or the moment magnitude scale, it's a 32-fold increase in energy. But we have a number difference of 2. So what do I do with 2 and the 32? Well, you do not times them by each other. It is not 32 times 2. It is not 64. What it actually is, the correct answer is C. The difference in magnitudes between the quakes becomes the exponent to 32, because it's an exponential or logarithmic scale, and that turns out to be something close to, I just rounded off here, around 1,000. So what I really want you to take away from this here is not so much getting it right or wrong, is that a magnitude 6 earthquake is 1,000 times bigger than a magnitude 4. Or in other words, you need 1,000 magnitude 4 quakes all combined together, going off all at once, to equal the energy of a magnitude 6. And that might hopefully that blows your mind, because I think everyone gets the feeling that, oh yeah, 8.1 is worse than a 7.6. But to understand really the difference, you subtract the difference, those two earthquakes, in terms of their difference, and turn that into the exponent to 32, and that gives you the energy difference between the quakes. So pretty fun stuff there, team. Hopefully you enjoyed this. We're going to do one more episode. The next episode, we'll wrap up this section on earthquakes. We're going to look at earthquake hazards, basically what earthquakes do that cause so much death and destruction. We'll look at liquefaction. We'll look at ground shaking, other secondary effects that go along with earthquakes. So thanks for joining me. Appreciate your time, and we'll see you next time.